So Green's theorem, up to now we've met two types of integration for functions of two variables. Okay, two types of integration for functions of two variables. We can either have some kind of region R in the plane, and we can perform a double integral over that region of a function of two variables of an f of xy, and we gave an interpretation to this as being the volume trapped beneath the surface above the xy plane and over the region R. The other type of integration we can do is going along curves in the plane. And here we talk about integrating a linear differential form, which is a function p dx plus q dy. And the p and q are functions of x and y, and we're integrating along the curve C. And this last section in Green's theorem draws a link between these two. So the question is there any kind of systematic or direct connection between these two types of integral? Well, there is. There is a kind of a one, and Green's theorem tells us how to relate these two types of integration and draw a strong connection between them. But first of all, we just introduce a bit of terminology. And so these things here are called path integrals or curve integrals. So we speak sometimes about closed path integrals. Closed path integral, well, this isn't a closed path integral, because here we've got an open path, a path which starts and ends at different points. But if your path begins and ends at the same point, it's called a closed path, such as this one. It's like a closed loop. Okay? So there's some point here along it, which is the start and end point. It's a closed loop, starts and ends at the same point. And there's just a slight adaptation to the integral notation. If you know the integral is over a closed path C, as an indicator to the reader, a helpful indication to the reader, we put a little circle in the middle of the integration sign. And that's just a signal to integrate that this is a closed path. And it just gives the reader some knowledge about the structure of the thing. So if your path C, however it looks, is closed, call this a path curly C. The path curly C is closed, then the line integral over curly C, if we want, and we should do, it's good practice, just put a circle around the middle of the integrations. It's just a signal to the reader. Like putting an arrow over a vector, there's no ultimate meaning to it. It doesn't mean anything. It inherently just indicates to the reader that that's a vector that you're looking at. So this just indicates to the reader that's an integral over a closed path. Now, with the properties we've already looked at for path integrals, we'll just remind ourselves of this fact that when you integrate along a curve but in the opposite direction, what's the meaning of minus C? So if C is a curve, minus C would indicate the traversal of C in the opposite direction to whatever the direction on C is, and that reverses the sign of the integral. Okay, so the integral over C is equal to minus the integral over minus C. So we're just reminding ourselves of that. Okay, and here in 1.22, we can give an example of a relatively straightforward closed path integral. We'll just consider the square between x and y, varies between 1 and 2, so does y. So we've got this square here, d to e to f to g. There's a little arrow here, so we're going anti-clockwise around that square. And we might integrate this linear differential form, 3x squared y squared dx plus 2xy dy. Okay, and you will find if you do that integration that you get the value minus 18. I won't go through it now, but it's just another application of this path integral technique. So the way to do it is to split the curve up into the 4 straight line segments: D to E along the bottom, E to F, F to G, G to D along the 4 sides. On each of those 4 straight line segments, the x and y variables behave quite simply. So for instance, on D to E, y is always fixed at the value 1. dy is equal to 0. The differential of y is equal to 0 along this bottom side. And x is varying from 1 up to 2. And similarly on the 4 other sides. One of the variables is fixed. So its differential is equal to 0. And it has a fixed constant value. So when you split up the integral as the integral over these 4 sides, each of the integrals of the linear differential form will reduce to just a straightforward integral of a single variable. Okay. This example also illustrates this phenomenon of path dependence. So when you do out these integrals, what you notice is that the 2 ways of getting from the bottom left corner to the top right corner, you can either go from D to F via E, so along the bottom and then up the right-hand side, or you can go from so sorry, that's a slight misprint here. This should be DGF here. DGF here. Go from D to F via G, D to G to F. And so these are 2 curves, so along the bottom and up the right, or up the left and across the top, 2 curves from D to F, for which the path integral takes different values, even though they have the same start point and the same end point. So that's an example of path dependence, where the value of the integral depends on the path taken from the same start point to the same end point. Again, we discussed that before, but I'm just reminding you of it now because it's going to occur. We're going to want to refer to it. The values you get are 13 and 31 respectively. And the value going around the curve will be DEF minus DGF. That's your 13 minus 31, which gives you the minus 18. Okay. So that's what an integral around a path, it's very simple example of a closed path would look like. So now we get to the situation where we're going to start to quote Green's theorem. And we've got some more terminology to introduce. The version of Green's theorem we're going to quote is, it's going to apply to regions like this here, so regions consisting of like a single blob. The version of it we're going to present it won't apply to regions which are made up of different components, different separated components. And just to get the mathematical terminology to talk about that, we say a subset of the plane we say is connected, or strictly speaking, we should say path connected. Path connected if any 2 points in the plane, if any 2 points in the region, this one and this one, can be joined by a path in the plane which is wholly contained in the region. So I can certainly get from this point to this point along a path like that. Even if the region looks a bit more complicated than that, this kind of region here, this still qualifies as being path connected. Even if I take a point over here and over here, okay, certainly not the straight line. If you take the straight line between them, that isn't contained within the region. It goes outside of the region in a few places. But there is a path which will take you between the 2 points, which is wholly contained in the region. Okay? Such a region is called connected, or strictly speaking, path connected. It's a slightly weaker topological notion of connectedness, which doesn't exactly correspond with being path connected. Now that's not quite enough, because this region could still be connected even if there was a hole in the middle of it. So if there was a bit in the middle of this region which was not part of the region, it would still be path connected. I could still get from any point to any other along the path within R. So for this one here, I wouldn't choose the straight line because that takes you outside of the region. But I could go around the hole and get from one point to another around the hole. So this would still be a path-connected region, but we want to exclude it from our discussion, from our statement of Green's theorem. And the way we do it is that this is an example of what's known as a region which is not simply connected. It is connected, but it's not simply connected. So a subset is called simply connected if the interior of every closed path in S is also contained in S. So if this is my region S that I'm referring to, there is a closed path here. This path here, which goes around the hole, that path, the interior of that path, considered as a subset of the plane, that does contain parts which are not in the region that we're talking about. So this region is not simply connected because it's got a hole in it. It's got a hole in it. So there are closed paths in that region whose interior is not completely contained within the region. So there's some diagrams over here on the right-hand side which kind of illustrate some of these. So that top shaded region here, this is not a connected region. Consider that as a single region. Well, it's certainly got two disconnected components. Okay, if you got a point in one blob and a point in the other blob, there's no path between the points which is wholly contained in the region. It has to go outside the region. This blob in the middle is connected, and it's simply connected. Okay, there are no holes in it. This one down here is connected, but it's not simply connected. Okay, because of the presence of this hole here in the region. These are terms from topology. So these concepts are examined rigorously in the subject of topology, and they connect to higher dimensional analogs of these properties as well. But with that terminology, we can now state, we can now look at our statement of Green's theorem. I will give an argument for the proof of Green's theorem. It won't be. It's not a completely rigorous argument, but it's be a good kind of sketch of the argument and an indication of why we should take the statement of Green's theorem as being true. So, okay, straight away you can see that, as I said in the introduction, Green's theorem does indeed give a link between the two types of integral. So on the left-hand side, without looking at the details of the integral, on the left-hand side, you recognize we've got an integral, we've got a path integral here. An integral over a closed curve, you see. On the right-hand side, we've got a double integral. An integral over a region subset of the plane R. So already you can see that it's that kind of a result. It's relating a certain path integral to a certain double integral. Now look at it a bit more closely. So R is a simply connected region of the plane. C is the boundary of the region R. Okay. So you see C is a closed contour. That's just another word for path or curve. C is a closed curve, and the simply connected region R enclosed by C. Okay. So R is going to be the simply connected region. C is going to be the boundary curve of it. And P and Q are the two functions appearing in the linear differential form on the left-hand side, and they are required to have continuous partial derivatives on the closed contour C and in the interior of C. So they're required to be well-behaved functions. And then Green's theorem says that these two integrals are equal. The integral, so this is your general integral of a linear differential form along the curve C, integral of p dx plus q dy. And what it's equal to is it's equal to the double integral over the interior of C, over the region enclosed by C, and you're integrating the difference of these two partial derivatives, dqx minus dp dy, and integrating those over over the region. And there's many applications. It's interesting because it connects the two types of integrals. Okay. So let's start thinking about how we might prove this and explain why it's true. Okay. So this is sketching the proof of Green's theorem. So what we'll do is we'll prove a simple case. We'll prove a simple case, and then we'll explain how knowing it's true on the simple case can be expanded and generalized to knowing it's true in general. Okay? So consider the rectangular region. Rectangular region R and its boundary C. So here it is, we're just talking about a simple rectangle, and it's aligned with the coordinate axes, with the y-axis, the x-axis. So its sides are parallel to the x and y axes respectively, and it goes between two limits, a and b, anything on the x-axis, and c and d on the y-axis. And C is the whole boundary curve, but we'll split it up into its components C1, C2, C3, and C4. C being the entire boundary curve. So the region R is the inside of this rectangle, and C. Remember what we mean by adding curves together. When we say adding curves together, we mean concatenating them is the technical term, running them together. If they fit together, if their start and end points fit together like that, when you add the curves together, you just mean running along them all. Okay. Okay, so let's look at consider the left-hand side of Green's theorem. Just called Green's theorem GT. So the left-hand side of GT, this is equal to the integral along C of p dx plus q dy. Okay, I'm not writing p of xy, q of xy. It's understood that p and q are functions of x and y. Just to save on the ink. Let's just write it down quicker. Okay, the normal way we'd approach such integrals is to split them up, to split it up as the sum of the four different integrals along each of the sides of the rectangle. C2 plus C3 plus the integral along C4. You're integrating the same thing each time. Again, I'll save ink. I won't bother writing it out millions of times. You know what I mean? We're integrating p dx plus q dy along each of the boundary straight sides separately, and then we're adding the results together. That gives us the integral around C. Now, if you look at what's happening along the boundary curves, it's very easy to describe what's happening with x and y. Along C1, y is fixed at C. dy is equal to 0, and x starts at A and then goes to B. You've got similar descriptions for each one. Along C2, x is fixed at B, dx is 0, and y goes from C to D. Along C3, y is now fixed at D. Again, dy is 0, so it's not changing. And x now begins at B and goes down to A. And along C4, finally, x is fixed at A, dx is 0, and y begins at D and goes down to C. So it's very easy to understand exactly what's happening with x and y on each of the four sides. So we can write down expressions for how each of these four integrals will simplify. So in the first integral, dy is equal to 0, so there will be no q dy bit. It's just all going to be rubbed out. So it's equal to 0 along C1. Y is fixed at C, and we're integrating x from A to B. So on C1, we're integrating x from A to B, and we're just integrating p of xc dx. Agreed? So there's no q dy bit appearing here, the integral for C1, because the dy is 0. Y is fixed at C, and we're integrating this function of x, p of x, and the constant c from A to B. Along C2, goes the other way. This time dx is 0, so there's no p dx. We just get a q term. X is fixed at b, so it's q of by dy, and y is integrating from c to d. That's the integral along C2. We have two more. Integral along C3, which is the integral of p x of d dx. And x is beginning at b, going to a. And finally, down C4, we're integrating q a of y, and y goes from d to c. Everybody agree with that? It's hard to progress it any further, really, because, well, I don't know what p and q are. I don't know what any of the values a, b, c, or d are. I'm keeping those general, okay? But this is how your left-hand side, it would simplify to that, okay? Because, so this is just all the consequences of because we're going along a rectangle aligned with the x and y axis, parallel to the x and y axis. Okay, so that's really good. Now we should look at the right-hand side of Green's theorem. Okay? And what we're going to prove is that it comes to exactly this. Okay? So we look at the right-hand side of it. The right-hand side is the double integral over R, which is the inside of the rectangle. We're integrating dq dx minus dp dy dx dy. And I'm going to do a few things with this. First of all, I'm going to use the linearity of the integration operator, indeed the linearity of the double integration operator, to say that this is just the double integral of dq dx dx dy over R minus the double integral over R dp dy dx dy. So that's just using linearity of integration. Well, then let's put in the limits of integration. So this is the integral yeah, on this one I'll keep the x as the inner integral and y is the outer integral. So y is going from c to d and x is going from a to b. But on the second one, I'm going to change the order of integration. So I'll now make y the inner integral and x the outer integral. So I'm changing the order for the second one. I'm making y the inner integral and x the outer integral. Now there's no problem. There's no obstruction to changing the order here. Remember, when the region is a rectangle aligned with the axes, you can freely interchange the two orders of integration. There's no funny business with the limits. You just swap the limits, keep the limits paired with their respective variable. So the outer integral is x, so that's integrating from a to b. The inner integral is y, that's integrating from c to d. Now the reason, why have I changed the integral on the second one? Well, I want to see, I'm integrating a derivative with respect to y. So now the inner integral will be just integrating the derivative with respect to y with respect to y. But those operations are inverses of each other. Differentiating with respect to y, integrating with respect to y. Those two operations are inverses to each other. So when you apply them both to p, you're just going to get p as the result. Similarly here, differentiating q and then integrating q, both with respect to the x variable, those two operations are inverses of each other. Differentiated, integrated. So this will just give me q here. So this will reduce to the integral from c to d. So I'll get q in the middle, but it's q evaluated at these limits, b y minus q of ay dy. Oh no, I did. It's okay. Thought I didn't start thought I didn't start recording. I did. Yeah, so you integrate and differentiate q, so you just get q, but it gets evaluated at the limits, so q of b minus q of a. But of course, q is a function of the two variables x and y. And then over there, the second part, you've got minus the integral from a to b, p of xd minus p of x c. Okay, so the justification like that is integration and differentiation properly interpreted with respect to the same variable, they're inverses of each other. The integral of the derivative is the original function. And now I can just split this up. Remember, I'm trying to show that it's the same thing as the left-hand side. So the left-hand side was the sum of those four integrals of p or q, and one of the variables was constant. Well, it's looking good. I've got two integrals of differences, and there's always one of the variables constant, so it's looking quite good. So this is integral c to d, q by. Now I have minus the integral of qay, but I can turn that into a plus by changing the order of limits. So d to c, qay, dy. So I'm using linearity here and swapping the limits, the upper and lower limit, which will change the sign of the integral. So that minus sign drops out. Then I'll swap those limits. So this integral of b to a, pxd, dx. And then I've got the double minus sign here, minus minus. So that becomes a plus integral a to b, pxc, dx. Okay, so that's what you get for the right-hand side. And then if you compare that to what you had a few minutes ago for the left-hand side, you'll see, hopefully, unless I've messed it up, you'll see it's exactly the same. Integral a to p. Yeah, it's exactly the same. So this equals the left-hand side of GT as required. So we proved the left-hand side is equal to the right-hand side. So we proved the Green's theorem for this simple case of a rectangle aligned with the coordinate axes. So GT is true for this region here. a rectangle aligned with the coordinate axes. Okay? But that's okay. That's a simple case. But of course, our regions aren't necessarily rectangles. They could have quite a complicated shape, and they could have quite a complicated boundary, although not too complicated, because remember we're only applying this to simply connected regions. So there's no holes in the regions. And if the region did have a hole in it, then its boundary would have two separate components. If I was talking about this region here, the boundary of it would be this boundary curve and this one. So it would have multiple components to the boundary. But if there isn't any holes in the region, and it's a simply connected region, then it will have this just single, nice, simple closed curve as its boundary. Okay, that's certainly not a rectangle. That's aligned with the coordinate axes. But, and here's how we get to the proof of the general case, we can approximate it with a load of rectangles. If I draw horizontal and vertical lines equally spaced across that region, suddenly you see, well, it is just a load of rectangles. Most of the time, the region is exactly just the union of all those rectangles. The only thing where things go a little bit wonky is around the boundary. So around the boundary will be the actual boundary curve of the region, and sometimes your little rectangles will miss a bit out, depending on where you've drawn your rectangles exactly. So sometimes there'll be little bits missing, and in other locations you might have your rectangles slightly poking outside of the region. If you've included rectangles like this, you've got you're straying outside the region. If you only include rectangles like this, then you're missing out bits of the region up here. Captured. It's just an expanded view of the boundary. But the idea is it's a pretty good approximation. That the integral over the region will just be the integral over all those rectangles. And as you allow the rectangles to become smaller and smaller, these errors, either the bits you've missed out or the bits you've included when you shouldn't have, you let the size of the rectangles, the diameter of the rectangles, or squares them, as you allow that to converge to 0, the error will converge to 0 as well. Okay. So for the general case, we can approximate such a region R by covering it in rectangles. Okay. Any errors of not including all of the region or including bits that aren't in the region, any errors will converge to 0 as the diameter of the rectangles converges to 0 also. If I allow my squares to become tiny and tiny and tiny, the error between the two will become 0. But what happens to the two types of integrals? Yeah, let's draw a bunch of rectangles here. Let's just say I've got this collection of rectangles. There's an interesting thing that happens when you integrate and you integrate around the boundary curves. Remember, by definition, we're integrating anti-clockwise. So if I integrate around all those rectangles anti-clockwise, what remains after integrating around all these rectangular curves? In other words, if I sum up all the integrals around these rectangular curves, remember, by default, we integrate anti-clockwise. And if you look at one of the interior edges, you end up integrating over it twice. So this edge here, once it's the top edge for this bottom rectangle, then we integrate along the edge right to left. But that edge is also the bottom edge for the rectangle above it. And then when you're integrating along it, you integrate along it left to right. So for every interior edge gets integrated along it twice, once in one direction and once in the opposite direction. Every interior edge gets integrated along it. Gets integrated along. For every interior edge, we integrate along it twice. Once in each direction. But you're integrating the same thing. You're integrating p dx plus q dy. So what happens when you add together those two integrals? When you integrate it once right to left, and the other time right to left, left to right, those two integrals will carry the opposite sign, okay? Because changing the direction along a curve reverses the sign of the integral. So all these integrals, when you're integrating around the boundary of all these rectangles, when you integrate along them all the edges are cancelled out. All the interior edges are cancelled out. Every edge which is part of the boundary of two rectangles gets cancelled out. All that's left once in each direction, which cancel out, leaving only the integral along the boundary. So the only thing that survives here will be the integral along the boundary. Okay. The integral along all the interior edges all gets cancelled out. So when you do these path integrals around the boundaries of a load of rectangles that are clumped together, what it comes to is just integrating along the boundary of the region covered by all the rectangles. And when you do the double integral over the interior of each rectangle, what you get is the double integral over the complete region covered by the rectangles. So the general proof so combining this special case,
Kelly, could you write down a bit, please?
Sorry. So if you combine the special case of a single rectangle with the behavior on a collection of neighboring rectangles, by which I mean this, a collection of neighboring rectangles,
Well, on the one hand, we're summing over all the rectangles the closed path integral around the boundary of one rectangle, p dx plus q dy. This will be equal to the sum over all the rectangles, the double integral over each rectangle, dq dx minus dp dy, dx dy. Okay, that we get from proving it, the special case for integrating over a single rectangle. So when you add up the double integrals over all the rectangles, you just get the integral over the whole region covered by the rectangles. When you add up all of these half integrals, you just get the half integral around the boundary of that region that you covered in rectangles. So this just gets to be the closed path integral. I mean, this is crazy notation, all right, but you know. The integral over the boundary of the rectangular region. P dx plus q dy. And this is equal to the double integral over the interior of that rectangular region. This is what I mean when I say we're giving a sketch proof. So we get Green's theorem on a single rectangle. By combining them together, we get Green's theorem on regions which have a rectangular boundary, regions that are made up of gluing a load of rectangles, similarly sized rectangles edge to edge. Just get the integral along the boundary. And then we have a convergence argument. This can be made into the integral along any curve, p dx plus q dy. And this can go to the integral over a region R, dq dx minus dp dy, dx dy. And the limiting thing here is as the size of the rectangles goes to 0. Same thing. So these arrows are convergence statements. As the size of the rectangles goes to 0, this integral will converge to the actual smooth boundary curve of the region, as we're covering this region with squares or rectangles that are getting smaller and smaller and smaller. And this integral over here, the integral around the blocky rectangular region, that will converge to the double integral over the interior R. Okay. And Green's theorem says that these two are equal. So the technical details that we're skimming over slightly is the technical details that say that if these two integrals here are the same, then as you take limits, the equality is preserved when you take the limit of the left-hand side and the limit of the right-hand side. So the technical details concern proving that the limit process, the limiting process is this integral converges to this one and this converges to that one. The limiting process preserves the equation, this equation up here, star, so that GT is true. Okay, but those are just the technical details surrounding how to handle limits of integrals. So we can understand now why Green's theorem is true. Okay. can be shown directly to be true for a simple rectangle lined with the axes. And then with the observation that any region at all could be approximated by gluing together a load of small rectangles. Okay. That introduces errors. Sometimes you're not taking in all of the region. Sometimes you're taking in parts which are not in the region. But as the size of these rectangles shrinks, it gets arbitrarily small, the error will converge to 0. And if the equation is true for any of the blocky regions, as we take limits, the equation will still be true, and that will give us Green's theorem in the limit. Okay, so you'll find applications of this in exercises 1.8. So you should consider exercises 1.8 in the tutorials. They're mostly just calculation examples around applying Green's theorem to various regions and confirming that it's true, verifying that it's true for certain regions. Okay, we'll finish there for now. As I've said, you will find me in my office later this afternoon or tomorrow. And if you've got any last minute queries.